So let's do an example. Where we can calculate from the beginning to the end everything. Now, you have to get accustomed to the idea that even though you can calculate everything, your formulas that you get sometimes are a little big. And you look at them and they may not tell you too much unless you plot them with a computer. So we push the calculations to some degree, and then at some point we decide to plot things using a computer and get some insight on what's happening. So here's the example. We have a potential up to distance a. Here is 0. The wall is always there. And this number is minus V naught. So it's a well, a potential well. And we are producing energy eigenstates that come in here. And the question now is to really calculate the solution so that we can really calculate the phase shift. We know how the solution should read, but unless you do a real calculation, you cannot get the phase shift. So that's what we want to do. So for that, we have to solve the Schrödinger equation. Psi of x is equal to what? Well, there's a discontinuity, so we probably have to write an ansatz in which we have a solution in one piece and a solution in the other piece. But then we say, oh, we wrote the solution in the outside piece already. It is known. It's always the same. It's universal. I don't have to think. I just write this. E to the I delta. I don't know what delta is, but that's the ansatz. E to the I delta sine kx plus delta should be the solution for x greater than a. Okay. You know, if you were not using that ansatz that has all the relevant information for the problem, time delays, everything, you would simply write some superposition of e to the ikx and e to the minus ikx with two coefficients. On the other hand, here, we will have, again, a wave. Now it could be maybe an e to the ikx or an e to the minus ikx. Neither one is very good because the wave function must vanish at x equals 0. And in fact, the k that represents the kinetic energy here, k is always related to E by the standard quantity, k squared equal 2me over h squared, or E equal the famous formula. On the other hand, there's a different k here because you have different kinetic energy. There must be a k prime here, which is 2me plus v naught. That's the total kinetic energy over h squared. And yes, the solutions could be e to the ik prime x, e to the minus ik prime x, minus I k prime x. But since they must vanish at 0, should be a sine function. So the only thing we can have here is a sine of k prime x for x less than a, and a coefficient. You know, we didn't put the additional normalization here. We don't want to put that, but then we must put the number here, so I'll put it here. That's the ansatz, and that's k and k prime. Now we have boundary conditions at x equals a, so psi continuous at x equals a, what does it give you? It gives you a sine of ka is equal to e to the I delta sine of ka plus delta. And psi prime continuous at x equals a will give me ak cosine ka equal, I have primes missing, I'm sorry, primes, equals k e to the I delta cosine ka plus delta. Okay, what do we care for? Basically, we care for delta. That's what we want to find out, because delta tells us all about the physics of the scattering, tells us about the scattering amplitude, sine squared delta, tells us about the time delay, and let's calculate it. Well, one way to calculate it is to take a ratio of these two equations so that you get rid of the a constant. So from that side of the equation, you get k cotangent of ka plus delta is equal to k prime cotangent of k prime a. Or cotangent of ka plus delta is k prime over k. I will erase this. And now you can do two things. You can display some trigonometric wizardry, or you say, okay, delta is arc cotangent of this minus Ka. That is okay, but it's not ideal. It's better to do a little bit of trigonometric identities. And the identity that is relevant is the identity for cotangent of A plus B is cot A cot B minus 1 over cot A plus cot B. So from here, you have that this expression is cot Ka cot delta minus 1 over cot Ka plus cot delta. And now, equating left-hand side to this right-hand side, you can solve for cotangent of delta. So cotangent of delta can be solved for, and here's the answer. Cot delta is equal to tan Ka plus K prime over K cot K prime A over 1 minus K prime over K cot K prime A tan Ka. Now, who would box such a complicated equation? Well, it can't be simplified anymore. I'm sorry, that's the best we can do.